All right, in this section we're going to examine how to represent points and curves using the polar coordinate system. Now, way back, if you think way back to when you took pre-calc. If you took pre-calc here at Vermont Tech, we spent a bit of time working with vectors and complex numbers, seeing how complex numbers were vectors. And we said that one of the things we could do was represent a complex number as though it's a vector, right? We define its how far from the origin it is and what its angle is as measured from the positive x-axis. And we called that a polar form. And that's basically, if you think about how we represented, wrote out a polar form for complex numbers, that's basically what we're doing here, right? We're thinking of a point on the curve, or we're thinking of a point in the plane, and just going to define it by its distance from the origin and an angle. So to construct the polar coordinate system, we start with a fixed point. We call it the origin or the pole. And we draw from the origin an initial ray. Then that's our starting point. Usually that initial ray is drawn as the positive x-axis, and we call that the polar axis, okay? So the polar axis, I just think of the polar axis as always being, I always draw it as the positive x-axis. Then each point in the plane is determined by its polar coordinates. Now with polar coordinates, we represent those coordinates as an ordered pair, just like we do with xy coordinates, only the polar coordinates are a value for r, followed by a value for theta. R is always first. R is the directed distance from the origin to the point, and theta is the directed angle from the polar axis to the ray OP. So here's some examples. We've drawn some polar axes here. So in all of these, I'm just going to draw out, this is in blue. There's the polar axis in all of these. And then we've drawn some radial lines, so these sort of concentric circles where r takes on the same value for each of those circles. And in this case, r is a directed distance. Now that's different. That's a little bit different than how we would represent complex numbers in polar form and how we represented vectors. In those cases, r was always positive. But since r is a directed distance, you actually could have a negative value for r. We just have to interpret what that means. So here, we'll start out simple. In the first figure, this right here, that's the point 2 pi over 3, meaning it's 2 units away from the center, from the origin or the pole, all right, which is why it's on that circle of radius 2, at an angle of pi over 3. So this angle here is pi over 3. And up here it says theta equals pi over 3. That means every point on this line that I'm outlining in red here makes an angle of pi over 3. So theta equals a constant is actually, in the polar coordinate system, theta equals a constant is a straight line going through the pole, going through the origin. Theta is also a directed angle, so we allow negative angles. If it's a negative angle, you start at the polar axis and go clockwise instead of counterclockwise. So here, this is the point in the middle figure here. This point here has polar coordinates 3, negative pi over 6. And because that's pi over 6 below the polar axis. But it could also be 3, 11 pi over 6. And actually, I think that's a typo. That should be a positive, 11 pi over 6. So I could think of it as going positive, 11 pi over 6 around in that direction, or backwards. So these both describe the same point, all right? And again, that should be a positive 11 pi over 6. So these last two figures, right, we could see that the same point can be represented in these two different ways. In fact, it can be represented in basically infinitely many ways. I mean, take any angle, add 2 pi to it, and you're at the same spot, right? Just make a full rotation. So r theta and r theta plus 2 pi, those are going to represent the 2 point. And because r is a directed distance, then making r negative is the same as adding pi to an angle, so you can counteract that by adjusting the angle by pi radians as well. And so actually I bet up here, while this is as written right here, that is a typo. It should be positive 11 pi over 6, but that could also be negative 3, and what is 11 pi over 6 plus pi is 17 pi over 6, or 11 pi over 6 minus pi is 5 pi over 6. Right, so there are multiple ways to represent the same point. What that negative does in front of r is it just sort of flips it across the origin. So positive 3 at 5 pi over 6 would be right here. And then making it negative just says, oh, flip it across the origin, make it go kind of backwards. And that's why that lands you at the same spot right there. So again, because of this, we end up really with, I guess, infinitely many ways to represent the same point, and sort of outlined right here. I usually, more often than not, will take a positive r and a standard position angle, like between 0 and 2 pi positive, unless there's a convenient reason not to. So we're going to start, we're going to do some problems. We're going to start with just some coordinate conversion, going back and forth between polar coordinates and the rectangular coordinates. So now, again, just think about vectors on the plane, right? So if I have, here are my xy axes, right? So not just the polar coordinates, but like think about putting xy axes on top, and I have a vector. Right, here's my vector. So think back to pre-calc, and we did some vectors in calculus as well. And maybe also, I'm sure you did them in physics. But, this vector is defined by its magnitude and direction, right? And it had coordinates vx and vy. Now, I'm just going through this, kind of doing a little bit of review of this vector components, because it's going to make Theorem 37 make a lot of sense. So this Vx, you'll recall, was always given by r cosine theta. And in fact, you can show that yourself using SOHCAHTOA, using right triangle trig. And Vy, the y component, was r sine theta. And so those components are just the actual x and y coordinates of the point where the vector ends. And that leads us right to this part here of Theorem 37. If I know the polar coordinates, if I know r and theta, I can get the x coordinate by taking r cosine theta and the y coordinate by taking r sine theta. If I know the rectangular coordinates, I can get theta by using the relationship that tan theta is equal to y over x, and then use the arctan function, and then making sure that we make any adjustments we need to locate it in the correct quadrant. And then Pythagoras, r squared is x squared plus y squared. And again, that's all from SOHCAHTOA and Pythagoras up here. So in example 6.6, we've got a couple of problems here. In each, they give us the they give us the polar coordinates. We want to find the rectangular coordinates. So let's start with part A. Our polar coordinates are 2, pi. Oops, so x is r cosine pi, r cosine theta, which is 2 cosine pi. Cosine pi is -1, so that'll give us -2. And y is equal to r sine theta, so that's 2 sine of pi. Sine of pi is 0, so we get a y coordinate of 0, and that means that our xy point is -2, 0. And now that we're working with polar coordinates and rectangular coordinates, it's actually pretty important to specify, like this part here where we say the xy point is -2, 0. That's important, right? Here they told us that the r theta point was 2 pi. So we want to make sure that we're really clear, communicating clearly whether a point we're giving is in polar coordinates or rectangular coordinates. Let's do another one. In part B, x is r cosine theta. So that is √3 cosine of pi over 6. Cosine of pi over 6 is √3 over 2. And so we get an x coordinate of 3/2. Y is r sine theta, so that's √3 times sine pi over 6. Sine pi over 6 is 1/2, so we get √3 over 2. And that means that our rectangular coordinates are 3/2 √3 over 2. Okay, let's try going the other way. In part A of this example, they give us the rectangular coordinates -1, 1. Now, a lot of the time, it can help to maybe just do a quick sketch, right? It takes very little work, very little energy to just plot this point, -1, 1. And so what we want is r and theta. If I'm starting with the rectangular coordinates like I am right now and finding polar coordinates, that's really, I pretty much always will just plot that point. I need to be really careful and mindful about what quadrant this point is in. It doesn't affect r so much, right? For r, we use Pythagoras as square root of x squared plus y squared. So we get the square root of 2. But what it does is it affects your angle theta. Now, the arctan function is not going to give you a second quadrant angle. So what we're going to do, we're going to find this acute angle here, which I'll call, I guess alpha, like a reference angle. And then I'm going to subtract that from 180 because this is in quadrant 2. Hopefully this is a little familiar. We've done this in pre-calc and a little bit in calculus. So theta is in quadrant 2. So that reference angle is given by arctan of the absolute value of y over x, right? If you just make your coordinates positive. So this is, I keep saying I'm subtracting from 180, but we're using radians, so I'm going to subtract from pi. Arctan of 1. Arctan of 1 is pi over 4. So we get 3 pi over 4. And that means that our polar coordinates, our theta, is √2, 3 pi over 4. All right, let's try another one. In part B, the polar coordinates they give us are, not polar coordinates, sorry, rectangular coordinates that they give us are 0, 2. So we're going to start by plotting them. 0, 2 is just right here. This is actually going to take very little work. We could really just do it by observation, right, by inspection. Clearly, I think it's pretty clear, r is equal to 2. That's 2 units away from the origin. And this angle, well, that's pi over 2. So sometimes things can be simple, and we will strive not to make them any harder than they need to be. So we've been working with polar coordinates, and we've talked a little bit about polar graphs. We talked about the radial lines, those concentric circles. And sometimes for a simple polar equation, we can get a graph just by using some geometric intuition and a little bit of algebra. So, and that's what we want to do in example 6.8. These will all be fairly simple. And then a lot of the time, for a lot of polar graphs, we really are going to need to just throw them in the calculator. I'll show you how to do that as well, and because our calculators have a polar mode. So in 6.8, though, we could do these sort of by inspection and using our geometry skills. So we want to describe the graph and confirm by converting to a rectangular equation. So in part A, r is equal to 2, right? The distance from the origin is 2 and doesn't change, right? So these are r equals 2. These are all points 2 units from the pole. So that means it's a circle, radius 2, center 0, 0. And if r is always equal to 2, we could just sort of use what we know about circles and what that equation should look like, but it's also in keeping with, if I know the value of r, then I'm just going to use this equation right here. Right, r is always constant, so that means x squared plus y squared is constant at r squared. In part B, we're looking at the equation theta equals pi over 3. So theta is fixed. So these are all the points on a line that make an angle of pi over 3 with the polar axis, or with the positive x-axis. So we've described it. We know what it looks like. There's our pi over 3. Now it also extends in this direction because r could be negative, right? So it really is the full line. Let's see, and it says convert to a rectangular equation. All right, well, if theta is constant at pi over 3, that means that tan pi over 3 takes on, tan theta is just tan of pi over 3. Tan of pi over 3 we know is y over x, right? Again, that is given in this formula here, right, in theorem 37. Tangent of pi over 3 is the square root of 3. So y over x is equal to root 3, and if we multiply both sides by x, we get y equals root 3 times x. And that is an equation of a line, right? It's with a slope of square root of 3. The last one is maybe less intuitive, all right? So in part A, r was fixed, so we saw that was a circle. In part B, theta is fixed, so we saw that was a straight line. Part C doesn't seem like anything's fixed, right? I mean, certainly it doesn't look like r is fixed and theta is not fixed, right? We have both variables in this equation. So we're going to use some algebra and what we know about these our trig functions. So we start with r equals secant theta. Now the reciprocal of secant is cosine. So multiply both sides of this equation by cosine theta. Then that tells me that on the left side I have, on the left side I've got r cosine theta. On the right side, secant times cosine, it's got to be 1 because they're reciprocals. R cosine theta, though, that's the x-coordinate. So this is the line x equals 1. It's a vertical line. Now that makes sense. You know, with a vertical line, we always think about something's fixed, right? Because the x-coordinate is fixed. It seems like it's, you know, super simple in that sense. But if we think about a vertical line in polar coordinates, well, certainly r is not fixed, right? Because that's changing. And also theta is not fixed because that is changing. It makes sense that to write an equation of a vertical line with in polar coordinates that both r and theta have to be allowed to vary. So these were some simple ones that we could kind of do just by maybe rewriting a little algebra, a little geometric intuition. But most polar graphs are not like that. And they'll be more labor intensive to sketch by hand. So if we can't take advantage of these, just some simple geometry, we can, you can certainly obtain a sketch by making a table of values for polar, you know, your polar coordinates, and that's pretty tedious. So for the most part, we're going to just throw equations in our calculator to help us out. So I'm just going to show you, we're going to go through one example here of doing that. We're going to get sketch a graph of 2 cosine 3 theta. This is called a rose curve, and once we see what the curve looks like, I think it'll make sense why we call it that. What we need to do first is put our calculator in polar mode. So I'm going to hit the mode button. Now down here in the last section, we put it in parametric mode. We're going to put our calculator in polar mode now. And when I hit y equals, I'm going to clear that out. Now when I hit y equals, now you can see that the equations look different. It's ready for equations that are written as r equals some function of theta. So we have 2 times cosine of 3 theta, so 3 times, and now when I hit my variable button, that automatically changes to a theta. And I guess I'm going to start just by graphing it on the standard window, minus 10 to 10 on the x and y axis, and I think I need to zoom in a little bit. So the x and y will go, let's see, I don't need them to get that big, so let's say from minus 3 to 3, minus 3 to 3, whoops. And then up here, just like we had with the parametric equations, I've got my theta parameter here. So I'll start theta at 0. Usually these polar equations involve trig functions, so I often start by just going up to 2 pi and seeing how that looks. And then my theta step, I think I chose pi over 12 maybe, and that's why it's that weird decimal. So let's see how this looks now. Okay, so it graphed that pretty fast, and this is called a rose curve just because we see each of these loops as like being petals of a flower. Now Now, the aspect ratio in calculators is not ideal, so it looks like it's not symmetric, but it is in fact symmetric, this curve. So we just sort of look at this curve and then try to do our best to sketch it by hand, and I'm never very good at it. So let's see. Looks like it goes out to +2, and in fact each of these distances out is 2 from the origin. So it does something like this, and that's sort of the best I can do. And I just sort of take solace in knowing that, well, my calculator can sketch it pretty well for me, and it does take some practice to try to get better at sketching polar curves. All right, so let's do a little bit of calculus. Let's talk about the slope and tangent lines. So here's sort of a generic polar curve over here on the right side. The function is r equals f of theta. And let's say we take up some point, r theta here, and we're interested in the slope of that tangent line. The slope of a tangent line in a plane is always a dy dx, okay? So it's always a dy dx, and now we have functions that are r as a function of theta, right? There's no y's or x's in there. So what we do first is remember that with the polar, how we get from the polar curve to the rectangular coordinates, just remember that x is equal to r cosine theta and y is r sine theta. And dy dx is dy d theta over dx d theta, just like with the parametric equations from the last section. It's basically just an extension of that same theorem. What we do when we think of the x and y coordinates as being given by these functions here is I just turn the polar coordinates into a set of parametric equations where the parameter is theta. So this part of the equation is nothing new, right? This is the same as what we used in the last section. Now, this part here on the right side of that equation, like it looks like maybe a complicated formula. I do not memorize that formula, but I just know where it comes from. And then once I realized where that formula came from, I wasn't worried about being able to find dy dx, because all we're doing to get these expressions in the fraction over here on the right side is we're just using the product rule on those equations. So, looking at this theorem, we'll note that we get horizontal tangents whenever dy d theta is 0, as long as dx d theta is not 0. We get vertical tangents whenever dx d theta is 0, as long as dy d theta is not 0. If dy d theta and dx d theta are both 0 for the same value of theta, then we don't know what's going on at the curve at that point. So we're going to do an example. We're going to find horizontal and vertical tangent lines for this curve. R is equal to sine theta on the interval from 0 to pi. Okay, so the first thing I need is the parametric form, right? I need to get the rectangular coordinates equations, which is just the parametric, represent this curve parametrically. So I know that x is r cosine theta, and I know that r is equal to sine theta, right? Like that's what they gave us. So this becomes sine theta cosine theta. that's x. Now, I know I'm going to find dx d theta, and I could go ahead and just use the product rule here, but sometimes you can make your work a little bit easier. If you use the double angle formula for sine here, you can rewrite this as 1/2 sine 2 theta, and then I don't have to use the product rule. So dx d theta, we get 1/2 times cosine 2 theta times 2, or just cosine 2 theta. Now we wanted to find the horizontal and vertical tangent lines. So vertical tangent lines come from where dx d theta is 0. And so I'm just going to set this equal to 0 to start getting solutions there, or at least candidates for solutions. So cosine 2 theta is 0. 2 theta is 0. Let's see. We're letting theta range from 0 to pi. So I got to let 2 theta range from 0 to 2 pi. Cosine is 0 at the top and the bottom of the circle, so that would be pi over 2, 3 pi over 2, and that means that theta is pi over 4, 3 pi over 4. Okay, so we have those are candidates for where we have vertical tangents. I say candidates and not definite because if I find that dy d theta is also 0 at one of these same values, then that's not necessarily a vertical tangent. All right, so that's for x. Let's do the same with y. Y is r sine theta. So that's sine theta times sine theta, or sine squared theta. And dy d theta, using the power rule here, is 2 sine theta cosine theta. And we could use the double angle formula for sine again. That's sine 2 theta. Looking for horizontal tangents, we're going to set this equal to 0. And again, if theta is going from 0 to pi, 2 theta is going to go from 0 to 2 pi. So 2 theta, sine is 0 at 0 and at pi, so that's it's 0, and at pi, and so that means that theta is 0 and pi over 2. Okay. So notice I didn't get any repeat values between each of these, setting dx d theta and dy d theta equal to 0. That's a good sign. That means that we will in fact have vertical tangents at both pi over 4 and 3 pi over 4. We'll get the horizontal tangents at both 0 and pi over 2. So now what we need to do is find r. So when theta is pi over 4, r is sine pi over 4. That's just the given function in the beginning. They said r equals sine theta. So that's root 2 over 2. At theta equals 3 pi over 4, r is sine 3 pi over 4. And at 3 pi over 4, that's also positive root 2 over 2. Okay, so we get our vertical tangents. At the points, let's see, these are polar coordinates, root 2 over 2, pi over 4, and root 2 over 2, 3 pi over 4. Now vertical, since they're vertical lines, we know they'll take on the form x equals a constant. So we know the vertical tangents happen here. If we want the equations of the lines, we simply get that using x equals r cosine theta. So that would be root 2 over 2 cosine pi over 4. And that'll give us 1/2 when we're done simplifying. And then here, x equals root 2 over 2 cosine 3 pi over 4. And that gives us x equals -1/2. So these are the polar coordinates where the tangents, the vertical tangents occur, and then we actually found the equations of the vertical lines themselves. Let's do the horizontal tangents now. We need to find r first. Again, we're just using the given function, r equals sine theta. So if theta is equal to 0, r is equal to sine 0, which is 0. And if theta is equal to pi over 2, r is equal to sine pi over 2, which is 1. So now, get our horizontal tangents at, let's see, these are polar coordinates, so r theta. So first at 0, 0, whoops. Oh, I lost one note. Hold on. Okay. These are polar coordinates, so at 0, 0, and at 1, pi over 2. And again, you could use y equals r sine theta to get the equations of the lines. We get y equals 0 and y equals 1. All right. Let's do one more example here. All right, so again, we're going to find the horizontal and vertical tangents for this line. We're going to start, we need the parametric form. So let's see, I think I'll just start with y this time. So y is equal to r sine theta. That's the basic form, right? That's how we get back and forth between polar and rectangular coordinates. So this is how we get the parametric form, which will help us allow us to find dy d theta. So r this time is 2 times 1 minus cosine theta, and times sine theta. And we just got to use the product rule here. I don't know that there's necessarily a really slick identity that will make it a lot easier to find the derivative. So, although I suppose you could multiply it out and maybe use a double angle formula, but I'm going to just go ahead and use the product rule here. First of all, I'm going to take this factor of 2 out, bring that down. So now we get 1 minus cosine theta times cosine theta plus, and then the derivative of 1 minus cosine is sine theta times sine theta. So we have 2 times, I'm going to try to simplify what's in the brackets here. We get cosine theta minus cosine squared theta plus sine squared theta. And we're looking for horizontal and vertical tangents. So we're looking at dy d theta to get horizontal tangents. Our whole point is to figure out where is this equal to 0. So that's what I want to move toward. I want to do things that'll make that easier. I'm going to use the double angle formula for, oh no, wait, I'm not going to use that right now. I'm going to use Pythagoras on this. And I'm going to write everything in terms of cosine. So that's 1 minus cosine squared theta. And let's see, what do we have? 2 times, I guess we have a minus 2 cosine squared theta plus cosine theta plus 1. I'm going to take out a -1 factor out of here. So I get a minus 2 times 2 cosine squared theta minus cosine theta minus 1. I'm doing that because I like seeing quadratics that have a positive leading coefficient. I just find that convenient. This is a quadratic. The stuff in the parentheses, that's a quadratic in cosine, and I think it might factor. So it'll be a 2 cosine theta times cosine theta, and then plus 1 minus 1. So that's how it factors. That's dy d theta. And it's helpful to write it this way because I'm interested in when dy d theta is equal to 0. So dy d theta is 0 either when this is 0 and 2 cosine theta plus 1 is 0 means that cosine theta is -1/2. And I guess I'm just going to let theta go. They didn't specify. I'm going to let theta go from 0 to 2 pi. So cosine is -1/2. That happens at 2 pi over 3 and at 4 pi over 3. And then it also, so let's see, that was the first factor being 0. We also get dy d theta to be 0 when this factor, cosine theta minus 1, is 0. And that happens when cosine theta is 1. And that happens at 0. And again, I'm just looking at this on the interval 0 to 2 pi, like including 0, but not including 2 pi, just because 2 pi is the same location as 0. So these are my candidates for horizontal tangents. Now let's work with the x equation. X is r cosine theta, so that will be 2 times 1 minus cosine theta times cosine theta. And I think this time I will distribute that cosine, so we get, and the 2, so we get 2 cosine theta minus 2 cosine squared theta. That's x, right? We haven't done any calculus yet. Now let's go ahead and find dx d theta. So we get minus 2 sine theta. And this will be, let's see, minus 4 cosine theta times a minus sine theta. We could simplify this to minus 2 sine theta plus 4 cosine theta sine theta. Now, again, we're interested, we're finding dy dx because it's going to help us find the vertical tangent lines. We want to get to a point where we can say, where is this equal to 0? And I don't think there's a horrible amount of work left to do that. We're in a pretty good spot here if we just maybe factor out 2 sine theta. If I factor out a 2 sine theta, then I get minus 1 plus 2 cosine theta, so I'm going to write that as 2 cosine theta minus 1. Now we can find where this is 0. It's in factored form, so dx d theta is equal to 0 means that either sine theta is 0, and that happens at 0 and pi, also, dx d theta will be 0 when, let's see, 2 cosine theta minus 1 is 0. That means that cosine theta is half, positive a half. And that would be at pi over 3 and 5 pi over 3. Now, here's one thing I want us to observe right away. This is why we find our candidates for both first, before we go through and find the value of r in the polar coordinates. Theta equals 0 occurs on both lists. So remember that if dx d theta and dy d theta are both 0 simultaneously, we cannot assume anything. Basically, we don't know anything about the slope at that point. Right, so that means it's inconclusive. What we could do is look at, I'm going to maybe just take a look at the graph here. I'm going to graph the curve here. 2 times 1 minus cosine theta. I'll start with that window. Okay, so theta equals 0, that's where it starts. And there's a cusp. Obviously, this curve gets bigger and I can adjust the window, but theta equals 0, that's what's going on right here. So there's kind of a cusp here of the curve. There's neither a vertical nor horizontal tangent line there. So we don't know what, we can't, I guess we could say that it's not continuously differentiable at that point. And I'm going to just adjust the window a little bit right now, maybe go out to -5. See if that's good. Okay, so there's a nice graph of this curve. Let's finish up the calculations we need to do. So we have all of our candidates, so we can't include 0 on either list. Let's start with the vertical tangents over here with dx d theta. Let's find r. So when theta is 2 pi over 3, r is 2 times 1 minus cosine of 2 pi over 3. And that'll give us a value of r equals 3. And at 4 pi over 3, and that will also give us a value of r equals 3. And you could work it out. You could find the coordinates on the unit circle to find cosine 2 pi over 3. You can also just throw it in the calculator. Make sure your calculator's in radian mode. So we have on the left side, that was, I think I said I was starting with the vertical tangents, but the left side, that's dy d theta, so this is horizontal tangents. So we get horizontal tangents at 3, 2 pi over 3, and again, these are polar coordinates, and 3, 4 pi over 3. Let's see, now let's move on to our vertical tangents. Let's find r when theta is pi over 3. R is 2 times 1 minus cosine pi over 3. And that'll give you an r of 1. When theta is pi, that'll give you an r of 4. And when theta is 5 pi over 3, and that gives us r of 1 as well. So we have our vertical tangents at these points at 1 pi over 3, again polar coordinates, 1 pi over 3, 4 pi, 1, 5 pi over 3. And this is borne out if we look at the curve, right? This is the way the curve looks. So let's say we take that point 1, 5 pi over 3. I'm going to hit trace, and I think if I just plug in a number, it'll take it as the value of theta. So 5 pi over 3, and that's right there. That's a vertical tangent. The pi over 3, that'll put me up here, right? So they're actually the same x equals line, right? And you could find that out, right? If you find the a vertical tangent is x equals a fixed value, and you'll see that x equals the same fixed value of both of those polar coordinates. And at 4 pi, at theta equals pi, there's that vertical tangent. And you could see the same thing. We have our two horizontal tangents up there and down there.